Hello everyone. Are you curious about how researchers measure ice thickness? Let's explore. Measuring ice thickness is a crucial aspect of understanding the dynamics of glaciers, ice sheets, and sea ice in polar regions like Antarctica and the Arctic. Accurate measurements of ice thickness provide valuable insights into the volume, mass, and behavior of ice masses, which are essential for studying climate change, sea level rise, and the impact of ice dynamics on global ecosystems and human populations. Researchers employ a variety of techniques and technologies to measure ice thickness, ranging from traditional methods like ice core drilling and ground-based surveys to advanced remote sensing techniques using satellites, aircraft, and unmanned aerial vehicles, UAVs. Each method has its advantages and limitations, and scientists often use a combination of approaches to obtain comprehensive data on ice thickness across different spatial and temporal scales. One of the most common methods for measuring ice thickness is ice core drilling, which involves extracting cylindrical cores of ice from the surface down to the bedrock or underlying substrate. Ice cores provide a record of past climate conditions, allowing scientists to reconstruct changes in temperature, precipitation, and atmospheric composition over time. By analyzing the layers of ice deposited over thousands of years, researchers can estimate the thickness of the ice sheet and infer the rate of ice accumulation and flow. Ice core drilling is typically conducted using specialized drilling equipment, such as ice augers, drills, or coring rigs, which can penetrate deep into the ice to collect samples for analysis. Ground-based surveys are another important technique for measuring ice thickness, particularly in regions where ice cores are not feasible or practical to obtain. Ground-based surveys involve traversing the surface of the ice sheet or glacier with radar, sonar, or other geophysical instruments to measure the thickness of the ice and map its underlying topography. Ground-penetrating radar, GPR, is a commonly used tool for ice thickness measurements, emitting high-frequency radio waves into the ice and measuring the time it takes for the waves to bounce back to the receiver. By analyzing the travel time and amplitude of the reflected signals, researchers can create detailed maps of ice thickness and bedrock topography beneath the ice sheet. In addition to ground-based surveys, researchers also use airborne and satellite remote sensing techniques to measure ice thickness over large areas and inaccessible terrain. Airborne surveys involve flying aircraft equipped with radar, LiDAR, or other remote sensing instruments over the ice sheet or glacier to collect data on ice thickness and surface elevation. Radar altimetry is a widely used technique for measuring ice thickness from aircraft and satellites, using radar signals to measure the height of the ice surface above the underlying bedrock. By comparing multiple radar measurements taken from different angles and locations, scientists can estimate the thickness of the ice and create three-dimensional maps of the ice sheet or glacier. Satellite remote sensing is another powerful tool for measuring ice thickness on a global scale, providing continuous coverage of polar regions and monitoring changes in ice volume over time. Satellites equipped with radar, LiDAR, or passive microwave sensors can penetrate through clouds and darkness to measure ice thickness from space. Synthetic aperture radar, SAR, is commonly used for satellite-based ice thickness measurements, emitting radar pulses towards the ice surface and measuring the time it takes for the signals to return. Microwave radiometry is another technique used to measure ice thickness from space, relying on the emission and absorption of microwave radiation by the ice to infer its thickness and properties. In recent years, advances in technology have led to the development of innovative techniques for measuring ice thickness, including unmanned aerial vehicles, UAVs, and autonomous underwater vehicles, AUVs. UAVs, or drones, equipped with radar, LiDAR, or photogrammetry sensors can fly over the ice surface to collect high-resolution data on ice thickness and topography. AUVs, on the other hand, can navigate beneath the ice sheet or glacier to map its thickness and basal topography using sonar or acoustic imaging techniques. These autonomous platforms offer new opportunities for researchers to study ice dynamics and monitor changes in polar ice thickness with unprecedented detail and efficiency. In conclusion, measuring ice thickness is a complex and challenging task that requires a combination of techniques and technologies. From traditional methods like ice core drilling and ground-based surveys to advanced remote sensing techniques using satellites, aircraft, and UAVs, researchers employ a variety of approaches to obtain comprehensive data on ice thickness in polar regions like Antarctica and the Arctic. By accurately measuring ice thickness and monitoring changes over time, scientists can improve our understanding of the cryosphere and its role in the Earth's climate system, informing predictions of future sea level rise and guiding efforts to mitigate the impacts of climate change on vulnerable polar environments. The goal of this channel is to answer all the questions in the world in video format. After we achieve it, when you search for anything on internet, you will be able to watch a video answering your question instead of reading an article. However, if we want to achieve our goal of answering 1 million questions, we need your help. Please support us on Patreon by using the link in the description. In exchange, we will feature your name in up to 1,000 videos every single month. Thank you for watching. Please like the video, follow the channel for more related content, and see you later. Goodbye.